Hi, this is Charles DiMaggio. Welcome back to R for Epidemiology. In this session, I want to introduce Poisson regression. And after linear regression and logistic regression, probably Poisson regression is the most frequently utilized regression tool in epidemiology. So I want to talk a little bit about what Poisson regression is, very briefly introduce, some ways to interpret it, and then just run through a quick example. Clearly, we're not going to have enough time in 10 or 15 minutes to really go into the kind of detail that you would need for Poisson regression early on. I just want to say that there are a number of different approaches to count data, Poisson regression being pretty much the entry approach. It's used a lot, but approaches like negative binomial and zero inflated Poisson are being used more increasingly to address some of the perceived issues or problems with Poisson regression. So to begin with, what is a Poisson model? What is Poisson regression? Well, classically, it's a regression model that's considered appropriate for count data, and it is a member of the general linear model family, where, as opposed to logistic regression, where there's a logistic link, it's a log link. And in the Poisson model, which can be representative, so it's like if y sub I is considered Poisson distributed and has a single parameter, theta sub I, what you see in the Poisson model is first that theta sub I, which is basically equal to mu, is equal to the variance as well, is also equal to the exponentiation of some predictor variable or set of predictor variables and their beta coefficients. That's a lot, all in one term. But basically what you need to know is that there's a single parameter in a Poisson regression, and it's a log link, so we exponentiate the results to get back at the linear model itself. And sometimes it makes sense in just sort of like thinking about it in terms of practical sense. So I think the conceptual hurdle in Poisson regression for epidemiologists is to think about how, when and where it should be applied. I tend to think about it in terms of almost like ecologic terms. So it's a matter of different units, each having a count of some kind of outcome. So the unit might be an individual who has various measurements over time. The unit might be a state. The unit might be by year. Frequently, you'll see Poisson regression used in epidemiologic studies of cohort data, where there are assessments over time. I work in injury epidemiology, so I tend to think in injury terms, in terms of my examples. But for example, you might think of traffic crashes at intersections, where each intersection can be considered the unit of interest, or unit sub I. So there are a number of intersections, and you're looking at the number of crashes over a year. And you might have a couple of explanatory variables like speed in miles per hour, or whether there is a traffic light at that intersection or not. And something like that might constitute a setting for Poisson regression. And we'll talk about that. Gelman and Hill actually present an example of that kind. One thing that you should note is that sometimes you get a little confused about when is Poisson regression appropriate, when is logistic regression appropriate. In general, if the number of counts or the number of successes is limited by the number of trials, so like, for example, you have some sort of outcome that's a count, and it's the number of successes and the number of times someone is ill or well. Generally, a binomial or logistic regression is standardly used. If, on the other hand, there's no natural limit to the number of outcomes, it's more standard to use Poisson regression. Also in Poisson regression, there is something called an offset variable. And the offset variable is really an underlying measure of exposure. And you can think of the offset variable basically as almost like a baseline predictor, okay? And classically what's done is you take the log of whatever the offset variable is. I'm trying to draw a nu there. And you could think of this variable right here as essentially a predictor where the regression coefficient is always set to 1. And it captures some measure of exposure. And that's sort of important for conducting regression. And what the nice thing about that is, especially in epidemiologic terms, it allows us to think in terms of incidence density ratios. Because if a beta coefficient in a regression, it can be seen as a ratio of 2, of holding the other coefficients stable, then it is in a sense an incidence density. So let's talk about a couple of ways you might use Poisson regression. And in Gelman and Hill's wonderful book on regression and multi-level modeling, they talk about a traffic crash model where they're looking at the effect of speed and traffic lights at intersections. And they present this model where y sub I, where y is the number of crashes at an intersection, I is some number of intersections, I believe it was in New York City, is considered Poisson distributed, and it is the model came out to be, and I'm going to just bring this down here it's Poisson distributed, and the model turns out to be e to the 2.8, where 2.8 is the intercept, plus 0.012 x1, xi sub 1, which is the presence, or which is speed at a particular intersection, plus, and I think the other one was, it would be minus, because it's protective, minus 0.2 times xi sub 2, where xi sub 2 is the presence or absence of a traffic light at an intersection. So how might you interpret something like that? Well, epidemiologists tend to interpret things in terms of causality. Gelman and Hill make a point of interpreting things in terms of predictive interpretation, which appeals to me, actually. And I kind of like the idea of it. But remember these three numbers. Here's the intercept. Here's the effect of speed. And here's the effect of a traffic light. So what do we do with that intercept? Well, it's 2.8 is this intercept. What does that mean? Well, that actually means the exponentiation of that is the crash rate when speed is 0 and there's no light. Essentially, it's uninterpretable. So we're really not going to interpret that intercept in this model. Now, the speed coefficient, which I mentioned, was 0.012. If you exponentiate that, this is on the log scale, so right? We're working on the log scale in the linear regression, but if you exponentiate that, 0.012, you end up with, I have it written down here, 1.012. Which essentially means that for each increase in a single mile per hour at an intersection, so 1 mile per hour increase equals an increase of about 1.2% in the rate of crashes, which sort of makes sense. It might make sense to take something like this and multiply it by 10, so that each 10 mile per hour increment results in a 12% increase in crash risk, but that's a matter of sort of like how to present this material. For the effect of a traffic light, we said that the beta coefficient for a traffic light was 0.20, actually minus 0.2. So the exponentiation of e to the minus 0.2, I'm not good at that, 0.20 basically results in an incidence density ratio of 0.82. So basically the presence of a traffic light at an intersection decreases the risk of injury by about 18%.